Hey there, Physics H. I'm going to follow up to this worksheet where we went over some of these bar diagrams. We went over two and then one on the back here. Kind of what we started with here, this gravitational, spring, and kinetic, kind of where they come from. So, turns out, as we're seeing in these bar diagrams, forces cause transfers in energy. Forces cause transfers in energy from one location to another. And it ends up being, so transfers in energy, we call it change in energy. So change in energy, and this could be any energy, right? This could be change in PE, G, change in PES, this could be change in kinetic energy, this could be change in E internal, change in E other. We change any of these by a force. And actually, it ends up being a force acting over some distance. So if you want to change something's kinetic energy, right, you apply a force to it, and it turns out the distance we apply that force for ends up causing the change in energy. It's pretty cool. So if it moves a meter, a force of 10 newtons, the change in energy ends up being force times distance. So if this is, let's say, 10 newtons over a distance of 1 meter, that ends up changing the energy by 10 newton meters. And that unit of a newton meter, newton times meter, we call a joule. Joule, which has the symbol of a capital J. So that's pretty cool. So we'd say the energy changed by 10 joules. And in this case, the applied force, the speed is going to increase. It would actually be change in kinetic energy equals force times distance. Well, this concept of force times distance and change in kinetic energy, we give that a name. We say that work was done. We say work was done. Work being change in kinetic energy. So work was done on the block overall because a force acted for a certain amount of distance. So maybe this was a person pushing the crate, right? And certainly, they would do work. That would take energy to move this big box 1 meter, right? So the equations that we get for these different forms of energy come from this concept of work being done. So the easiest one we can do is gravity, PEG, the equation for gravitational potential energy, right? Because if you think about something falling down, right, just a simple box starts off at rest, so it's all PEG, right? And then it gets converted, by the time it hits the ground, it's moving fast, it gets converted into KE, right? So it's going from PEG into KE. We could think about the bar diagrams if we wished here, right? The thing here is, how much did it change its height by? Right? Change in height. Turns out the gravitational potential energy, and technically the change in gravitational potential energy, ends up being the force that was applied to the block over the distance. Well, the distance it moved was delta H, so that's our distance, delta H, and the force that was applied was the force of gravity, which is mg. So as this thing falls, right, the gravitational energy is going to go down. And that's going to get converted into kinetic, right? So the overall change of gravitational energy is that. Now, typically what we do is we say, okay, I don't want the change, but I want the PEG just at this location. So the PEG at that location would be, it's mg times however far above its lowest point it is. So it would be mgh. So there's our first equation for energy. PG equals mgh. And that's a lowercase m, my bad. mgh. All right, so put that in the bank. Energy equations. PG equals mgh. Now, we're going to do a lab today with a spring. All right, and it turns out that spring force, right, when you have a spring, the spring applies a force to whatever is hung to it, and that's turns out it's proportional to something called kx. F of a spring equals negative, or equals, well, we'll just call it kx, not negative. Force of a spring equals kx, where k is going to be something called the spring constant, and x is how far the spring is compressed. All right. So if the object starts here, right? Let's say there's no, I haven't hung it on it. I've hung it on it, and it pulls it down to here, or I pull it down to here. I've stretched the spring by a distance of x, right? So if I do the change in energy here equals force times distance, well, the force here is kx, right? But and the distance is x. Now, it looks like it should be kx squared, right? If you go, but it turns out that this force, as it stretches, can't be constant, right? Because as you stretch it, this force is going to increase. So it can't just be force times distance. It turns out, and we'll see this in class today, and I'll show you in the lab why this is. Turns out that the spring energy stored, the change in energy when you stretch your spring, is 1/2 of kx squared. And I'll show you why the 1/2 comes into play in lab today. Now, typically, again, we don't call this change, we just call it PS equals 1/2 kx squared. Now, here's the thing. PES and PEG, they're easy to, get to using. Actually, to get this one, you would have to use calculus, believe it or not. You have to do something called an integral to get the spring potential, to derive the spring potential energy equation. So we're up to our two potential energy equations. It's force times distance, ultimately. PEG equals mgh, PES equals 1/2 kx squared. Now, the last one is kinetic energy. And that equals 1/2 of the mass of the object times its speed squared. Now, it looks a lot like this, and you think, I wonder if that's for a reason. Sort of. Not exactly, though. Sort of. Like, these two really don't have anything directly dependent on each other. But, so kinetic energy, you can also derive from force times distance, right? But what you have to do for that one is say, okay, so change in kinetic energy, right, would be force times distance. So the force here is equal to mass times acceleration, right? Whatever the mass is times however much is accelerated. The distance it travels, what they end up doing with this is we take time out of the equation and we use the v squared equation to solve for d. Right? So this is kind of a weird derivation here. And I don't expect you to memorize any of this other than the equations, okay? So if you're interested in where these equations for energy come from, it all comes from work, which is force times distance. But there's a little bit of arithmetic going on here, right? So really, at the end of the day, you have to know these equations. The derivation of these is fun, and you should know this one here. Actually, the work was done. We end up calling W equals change in energy equals force times distance. So really, you need to know that and that. The derivation's cool, though. There's some of you that might take an interest in physics and say, hey, this is kind of interesting. I'm interested in engineering and science. Maybe I want to learn a little bit about this derivation. Now, if you can show somebody how kinetic energy is derived later on in life, they might be very impressed, or not, but they might be impressed. So the D here, what we say is, okay, V initial, V final, D, what's the acceleration? All right, so D is the distance traveled, which usually we call delta x, right? So the v squared equation says v final squared equals v initial squared plus 2ad. All right. Let's say it started off from rest, right? So we just say that's 0. So we say v final equals 2ad. So d equals v final over 2a. So we put that in up here. We get ma times v, oh, I forgot the squared, v final squared over 2a. A's cancel. You get mv final squared over 2, which we can write as 1/2 mv final squared. So that's where the change in kinetic energy comes from, right? Or the gain in kinetic energy, or the kinetic energy at a particular location. Now, these energies represent the energy when system is in a specific state. You know, it's a snapshot in time and space. Like, what is the energy at a particular location? And what we're going to see is the energy at a particular location in a system, the total energy, it must remain constant. All right, so we're gonna gradually get there. So at the end of the day, again, what you need is work equals change in energy, is what we quantify it as being the force acting per distance. This is why I've said a few times that energy is really a product of force. But the reason we do it is because, you know, if we were to look at so go to this page. I'm going to copy down my energy equations. PEG equals mgh. PES equals 1/2 kx squared. KE equals 1/2 mv squared. Work equals change in energy equals force times distance. And again, this could be applied to any of these, the work one. If I was to look at that roller coaster one we had in class, right? And I said, okay, let's get rid of friction. All right, let's get rid of friction completely. All right, let's just say it starts off at rest. I let it go, and it reaches some speed at the bottom. I say, okay, give me the final speed at the bottom. Oh, yeah, well, let's see here. V average equals delta x over t, or V final equals V initial plus AT. So yeah, V final equals acceleration times time. That seems right. Well, what's the acceleration? Well, it's gravity. Well, the problem there is gravity acting to pull it forward, pull it down the ramp, is changing the whole time, right? Like, you would have to find the component of gravity parallel to the ramp, which, holy cow, I don't even know how to do that. Like, the acceleration isn't constant. Because it's a curved path, the acceleration changes the whole time. Even just looking at a object going down an incline, right? Just a straight incline. What's the acceleration? It's not g. G's trying to pull it straight down. The acceleration is the component of g that is parallel to the ramp, right? So when we did that lab early in the year with a cart on the ramp, the acceleration was like 3-point-something meters per second squared. It wasn't g. It wasn't 9.8 meters per second squared. It's because it's not getting pulled straight down. It's getting pulled at a component parallel to the ramp, which it's a pain, right? Like, a curved loop to try to figure out the acceleration is impossible. So what we do say is, okay, you know what? It's going from gravitational energy at the top, right? It's all gravity. Think about the bars, right? I know that this is 4 units of energy, PEG, at the top. At the bottom, the kinetic energy is 4 units. So that means I drew too many units there. That means the PEG at the top has to equal the KE at the bottom. All right? So we're going to take these bars that we made on the first worksheet, and we're going to use that conservation of energy principle to determine things like the speed at the bottom. So what you could do here now is say, okay, mg at the top, that's mgh, where the height of the ramp, right? And at the bottom, I have 1/2 mv squared. Oh, cool. So I can solve this for V now. And this is a really common result, actually. The V's cancel. You get 2GH equals V squared. So V equals radical 2GH, the speed at the bottom. It's not just simply, you know, acceleration times time or delta x over t or whatever. You know, it doesn't work that way. It comes out a little bit different than you would think. We've seen this before, believe it or not. So ultimately, this is what we're going to do. So first thing we're going to do, though, is just practice using these formulas on worksheet 2. Time we got? Oh, we got a minute left here. So on worksheet 2, all we're doing is calculating different energies at different locations, okay? So right on the top of this worksheet, I recommend writing those PEG equals MGH, PES equals 1/2 kx squared, KE equals 1/2 mv squared. All right, those are the ones you need, and work equals force times distance. And remember, work is change in one of these energies, change in energy. So a 0.5 kilogram block starts and rests on a 6 meter tall ramp. So that means this is 0.6 meters. Its height is 0.6 meters. Slides to the bottom. Determine the gravitational potential energy at the top of the ramp. So this is all we're doing. We're just going to practice using these formulas a little bit before we actually do the conservation of energy. So 0.5 kilograms times 10 newtons per kilogram for G. And, you know, no negative sign on that. You don't have negatives here unless we're taking away energy, which is a different story. We'll talk about that in a minute. And the height is 0.60 meters. So 10 times 5, 10 times 6, 0.6 is 6, times 0.5, half of 6 is 3.0. And look at kilograms cancel, you end up with Newton meters. Newton times meter, which is a joule. 3.0 joules, PEG at the top. So that means the kinetic energy at the bottom has got to be 3.0 joules. And we just go through practice. 2 kilogram block slid with initial speed of 12 meters per second comes to rest. Determine the kinetic energy of the block. Initially, that should read. So KE initial equals 1/2 mv squared. Equals 1/2 of 2.0 kilograms times 12 meters per second squared. Now, remember, it's squared. It's the whole thing squared, right? So the units on this, they do come out to be Newton meters, and you get 144 joules. You might get big energies, right? Depending on the mass and the speeds, you might get energies in the 10,000s, which is totally possible. So you're going to continue on trying to calculate these different energies. We'll go over these in class, have you do the solutions, look at the solutions, and we'll go from there. Now, in the next worksheet, we'll actually do the conservation, and then it's fun stuff, and then we'll talk a little bit more about work and power, and we'll be done. So hopefully we'll wrap this unit up before break, have a test before break. I'm going to end this video here. Have a good one.